Good afternoon. So in last class we discussed about X-ray diffraction techniques and how we can prepare the analysis of X-ray factor and all details we have discussed from the source detector, all those part we discussed. So today we'll discuss some few other XRD based techniques, X-ray based techniques, and if time permit, I'll also discuss about neutron diffraction. So today we'll mainly cover single crystal XRD, then grazing and single crystal XRD mainly used for single crystal samples, and then grazing angle XRD that we generally use for the thin film devices. Like if a thin film, you can do the X-ray analysis by using grazing angle technique. And then we have synchrotron XRD that will be mostly use high energy, highly monochromatic synchrotron radiation that you can use as a source instead of conventional XRD, and X-ray absorption spectroscopy that we will discuss with neutron diffraction. So first coming into single crystal XRD. So if you see in single crystal XRD and powder XRD, the basic difference is your mainly sampling, and then the sample rotation. That is one of the important thing in case of single crystal XRD. But in powder XRD, we see that two methods: one is theta to theta, another is theta theta diffraction techniques. If you go for theta theta technique, in one case that the sample is fixed, but source and detector is moving. But in case of single crystal XRD, your sample is also rotating here. So it's generally it is called a rotating crystal method, in which a single crystal is mounted with a normal to the axis. You can see here, this is a sample holder. So here, this is the X-ray source. From here to here, from the X-ray, this is X-ray source to the sample is here. And in this case, then you have transmitted that beam is coming here. You are getting a pattern here, the diffraction pattern. So here the sample is mounted with an axis normal to the monochromatic X-ray beam. So this is the X-ray beam is coming. So sample is mounted here perpendicularly, and then as crystal rotates, so here the important thing is your sample is also rotating. As crystal rotates, here that the stage is also rotating, your sample is also rotating, both source and detector both are moving. So here when the stage is rotating, so what happens? Many as crystal rotates, a set of lattice will meet some point to make a correct Bragg angle. That means in case of polycrystalline sample, you have many thousands of crystal in the material, but here it is a single crystal. But since it's rotating continuously, so what happened? A particular set of plane will at certain point that will make a certain Bragg's law satisfies, and you will see the diffraction pattern. By recording the diffraction pattern, both angle and intensity, that is similar to powder XRD of various crystal orientation, so you can get information about shape, size of the unit cell, as well as atomic arrangement, that is bond length, bond angle, side ordering. So generally in powder diffraction we get shape and size information of the unit cell, but in addition to that, in case of single crystal XRD, so we get atomic arrangement information, especially bond length, bond angles, as well as site ordering, whether it is coordinated with octahedrally, tetrahedrally, all those site ordering you will get information. So the single crystal XRD allows for absolute structure determination that can be identified unknown crystal. Like if you have unknown crystal, you can also identify by measuring this bond ordering, bond angle, all those shape, size. You can able to mostly get the electron density. From there you will able to find out the single crystal structure of an unknown compounds. So it's specified chamber. So you can also do high pressure or high temperature. X-ray diffraction can also be done in case of single crystal XRD. So as I told, the single crystal XRD is mainly is called a rotating crystal method. So here single crystal diffractometer uses 3 to 4 angle goniometer, 3 to 4 circle goniometer. You can see here this is the sample stage, that is omega rotation is here, sample stage is rotating like this. Okay, so then you have a sample, that sample is also rotating, rotation, and then you have a X-ray source here. You can see here this is the beam trap, the direct beam is trapping here. This is the diffracted beam. So here the diffracted beam to the detector, that is also, this is also moving. Okay, so you have what are the four angles? If you see 2 theta, one that diffractometer angle, that diffracted beam angle, then you have a chi, then you have a phi, and then you have a omega. So this omega is your stage rotation. So all those, you're rotating here. The samples are mounted on a thin glass fiber using epoxy or cement. So like in thin powder oxide diffraction, so what you take powder that mounted on a glass substrate or in the particular group that sample holder. So in that you put your sample and you are exposing to the X-ray. But here that sample, that crystal mounted on a thin glass fiber. So here it is mounted here in the center using some epoxy or cement that is the adhesive, which are attached to a brass pins and mounted onto the goniometer tip. So adjustment of X, Y, Z, that X axis, Y, and Z axis, all these three used to mount it in to adjustment of the beam to the centering to the beam with respect to the sample, and then beam stop that located directly opposite the collimator to block transmitted rays. Like if direct beam if you are seeing, so your detector is moving like this. Okay, so it's at certain time this will come in front of direct beam. So if direct beam falls on the detector, so this detector can burn out, it can cause damage. So to prevent that, there is a beam trap at the opposite out of the incident beam. So if something passes out, it will immediately stop that. It will allow only that diffracted beam will be allowed. So specifically the main difference that here sample stage rotation and the source detector, all those rotation. So if you see in single crystal XRD, in modern day XRD, if you see that uses charge coupled detector. Like in the earlier stage, I told that there is a 2D detector, there are this 1D and 2, that line detector or a spot point detectors. But here mainly the 2D detector, that's a charged coupled detector is used. So to use CCD to transform what are the X-ray photon into an electrical signal. Like here the sample is here, the X-ray is coming, then it's diffracted in different angle, and then there is the intensity IK, so that will be converted using a Fourier transform equation. So that will convert it to into a electron density map you will able to get. And from this electron density map, depending upon the electron density, whether it's a chlorine atom or the carbon atom or is a sulfur atom, whatever may be, depending upon the electron density, there will be different types of spot you will see. So finally, you can do with atomic modeling, you can predict the unknown structures. So here that in the X-ray photon into an electrical signal, which are then sent to the computer for processing. So diffraction pattern at each angle can be huge to produce a 3D electronic structure you can get. So the limitation is mainly, so you must have a single crystal. You can't do a powder sample or a polycrystalline sample you take and do a single crystal, etc. That's not feasible. So your sample has to be single crystal. It has to be robust, stable samples. And generally, they're quite large size. So you have to size of about 50 to 250 micron in size. And then, since this you are doing X-ray diffraction analysis, the sample has to be optically clear. There should not be any defect centers or the obstacles inside that, so it's optically clear, and twin sample can be handled. Like if a sample that is having twin, there's some surface is broken or is a twin, so you have to handle carefully. And then data collection, if you see normal XRD, like powder XRD, as I told, conventional powder XRD, in few minutes, like 5 to even 15 minutes scan will give a very good result. But in case of thin film XCD, single crystal XRD, you have data collection require 24 to 72 hours minimum it requirement. So once you get the information about the electronic structure, so you can refinement can be done using different software like powder XRD. Generally will use full food. Here there is SLX and OLEX2 softwares are available to analyze this type of X-ray analysis, single crystal X-ray analysis. So I'll just give one or two
Sir,
example. Yes, yes,
sir,
yes. Tell me.
Sir, can you please go back to the previous slide? I have a question.
Yeah, yeah, tell me.
Sir, do we do the Fourier transform by passing it through a lens which acts as the Fourier transform when we study holography, or do we, like the software you mentioned, do we feed the diffraction data to the software and it does it for us?
Yeah, software does it actually. So in that X-ray software itself, once you get the data is recorded, the software that do the Fourier transformation, and you can get it the result.
But
Otherwise,
was it done before the software using lens, a
no, no,
system
no.
of lenses or something?
No, that this all these things after analysis you can after during data recording itself it has to do through the software.
Okay.
Not like once you collect the data, then you take do in other software. That's not possible. So it is
Okay.
mostly it is done inbuilt. That software is with association with the instrument. It will simultaneously do that work.
But sir,
Okay.
why cannot it be done after the experiment? Because we already have all the data collected. We only
Yeah.
need the data.
Yeah, that is correct. But see, once passing through detector, so what happened that you will get some spots and all these things. So once you transfer, and there may be some losses, all these things. So better this is an inbuilt software with that with the instrument. Like if you see some of the microscopy things there, the software does it inbuilt. Okay, so
Okay.
you can do it later on, but the better result you will be if the Fourier transform if you do inside. Like in case of FTIR spectroscopy, if you see the Fourier transform itself done inside that that interferogram. Okay, so similarly it's here also. Okay, so if you see one example, I'll just discuss that DNA. All of you know that DNA crystal structure was developed by solved by Watson and Crick. So they have used this single crystal analysis. So initially that Rosalind Franklin, a physical chemist and a crystallographer who first taken a photograph of BDNA. So they have taken this photograph, the photo 51. If you see that XRD image that Watson Crick to show you this photo, this diagram they have taken. That this is that called it a photograph for a BDNA, that bound DNA structure. Then Watson Crick, who combined the information from this photo 51 and molecular modeling structure. So both they have utilized both the structure and they analyzed this photo 51. So what that initially you can see that there is a X pattern. What are the pattern you are getting? It is a X pattern, and then the X pattern, and then it's the whole pattern is a diamond shape. If you see inside the X pattern, so these are some diamond space they got, and then there is they get the different there are some few lines they got inside the photograph, and then this particular here it is a missing plane, here it is a missing they got. Then this missing plane is mainly that even how they solve once they got this plane this shear span. So this plane that reveals that there is a intercalating structure, that double helix structure, that the missing plane clearly indicate that the two helix overlapping at certain point. So that's why you are getting the missing structure, and then they utilize that missing whole structure and bound that for the information like this pattern they got a double helix, the radius, all those thing parameters they got, and then combined with data with other information like DNA made up of sugar, phosphate, nucleotide attack, SCGT, all those structure they got, and then this Chargaff's rule that to be that's a percentage of AT is equal to percentage of adenosine is equal to percentage of tyrosine, and guanosine is equal to cytosine. So and by this structure they predict this model DNA crystal structure, helical structure by using this single crystal XRT. So this is another example. This is a monoclinic structure, unknown crystal structure of which is a carbon 32 with this is equal to tellurium platinum complex with chlorine. So in that case, so after this XRD structure we get, so atomic size X, Y, Z coordinate you can get, and then by measuring the cell angle that and the length, bond length, all these things, you can predict the structure of this crystal structure. So you mainly will get a crystal that pattern. So that from the pattern you have to get electron density like platinum. Platinum has a high electron density, and tellurium, then chlorine. So accordingly, depending upon the electron density, you can identify those elements, and then you can finally predict the structures. So that was just I have given a little bit introduction to single crystal XRD. So if you have a thin film sample, but thin film sample like you have a substrate, like for example you have a silicon substrate. On a silicon substrate you put some thin layer, for example indium or some solar cell you produce layer by layer solar cell structure. So those type of the thickness of the solar cell, whether the top surface is perfectly formed or not. To see those things we need a thin film XRD. So that is called grazing angle XRD. So that we will discuss what is grazing angle XRD. So you can see here, this is a substrate. The green part, this is a substrate. On this substrate, you have a thin film coating, the orange color I have put here. So you can see this is quite thin comparison to your substrate. So if you take a powder XRD, what will happen, like theta will come from like this angle. So there is a probability now what happens that it can be touched to the substrate. So if the X-ray diffraction beam goes up to the substrate being thin film, so you will get the substrate signal. So you have to remove, it is difficult to remove the substrate signal from a conventional powder XRD. So in order to get only thin film, the XRD from only this portion, only from the thin film, so you have to go for the grazing angle XRD. So incident angle here is very small. So instead of this big theta value, this like normal XRD will take 10 to 140 degree to 2 theta you can go, but here our theta value is very less, only less than 0.5, less than 5 degree. So X-ray, so that it will come like this. So X-ray will mainly focus on the top surface. So this X-ray will not, it will have to cross this much path length. This much path length, then it will come to the substrate. Okay, so because of this long path length, so what happened, the exergy energy is such a way that it will not penetrate to the substrate, so it will come from the thin film. So GA-XRD can perform in many analysis possible with PXRD with added ability to information the depth profiling. So you can get a depth profiling here. So mainly from the top surface you will get the information. So you can orient it or thin film, your sample can be slightly oriented depending, you can change, like if you have a sample you mounted here, like thin film you want to take, you can rotate the sample like this. So by rotating the sample orientation, you can get, adjust the position to get the better, X-ray pattern from the film, and that if there is a lattice mismatch between film and substrate, those information you can get. There is a structure unidirectional growth, like particular growth in a particular epitaxy, that one direction, that information you can get. Substrate and thin film, but the microstrain built up between that information you get. And you can also do that grazing angle reflexivity measurement. So you can get that, roughness, thickness, density of the film, all those you can measure using X-ray grazing angle XRD. So this technique doesn't require any crystalline film. It works even in amorphous film also. You can get some information. So if you see here, you can see that this is my substrate, the orange one. Then the different angular beam I have followed it. There is red, blue, green, and violet beams. If you see, the mainly this all the bottom one, that pink, slightly that pink color beam, it's spreading over the sample surface, top surface. So mainly that you can get the weak signal, like you can easily get that diffraction pattern. But only the problem is, since its angle is very less, so your interaction of the electron beam with the substrate will be weak. So you will mostly the weak signal from the ultra thin film. So in that case, so GI-XRD geometry increases. You can do perfect positioning of the sample to get better thin layer signal, and overlapping peak can be possible in this case because it's a very thin film that you can see that if you want to get this grain structure with a powder sample, you may get some other signal also. But if in case of single crystal, there is no issue. But the problem is that there is overlapping is possible. Stress and measurement you can also do, and it is texture analysis you can do. You can see here, this is the one peak you are getting first. This one, that the one plane, this particular plane is falling with the XRD. Now you tilted the sample substrate in such a way, instead of falling this, the sample is falling in another, that incident ray is falling on another crystal. So you will get additional peak for that. And if you slightly rotate your 2 theta position, theta angle, as well as some substrate, you can see some other crystal you can identify, you can get that peak also. So similarly, you can get many peaks from the thin film XRD. So the instrumentation is almost similar to that of that powder XRD. You see that there is a sample, and then here is a X-ray source. From X-ray source, the incident ray is falling here. Then it's coming to the flat monochromator and before going to detector. So the only thing is the angle of incident is less than about 5 degree here. So but the rest of the things are almost same. So if you see the thin film XRD and conventional XRD, you can see that the bottom one, that this light blue color, sky blue color X-ray peak, you see this particular peak. So this particular peak is taken by a conventional XRD. So in conventional XRD, you see that peak intensity is very, very low. And these other peaks you are not getting any other peak. But same thing if you go for a grazing angle XRD, for a thin film sample, you see how the unattached phase is of PiO2 photocatalyst showing such a strong peak, and additional other peaks you are able to see. So for thin film, it's best to go for a low angle with grazing angle XRD. So you can also do that conventional XRD, you can use to do this grazing angle XRD if your angle, the instrument can go to such a low angle. Generally in the conventional XRD from 10 degree onwards, but some of the new XRD now conventional XRD coming with grazing angle XRD, there is possible. So you can see another example here. In this example, you can see how the peak intensity also this green one, that is from this grazing angle XRD. So you can see the difference, how the peak intensity. So you see here in case of conventional green one, and in case of blue and black, that is grazing angle, you can see so many additional peaks, you can able to see all things. So in normal XRD, you need a large proportion of diffractogram comes from the substrate. But in case of grazing angle XRD, so only the diffraction will coming from a small area, like in from the top surface is coming. So you have to, it take little more time, and then you need a highly sensitive detector to detect that. So you can see, you can get if a layer structure, for example, a thin film structure like a solar cell. In solar cell, you have a like molybdenum substrate, then CIGS, some coating agent, then zinc oxide on the top surface. These are the multi-layer structure. So the multi-layer information you can get by using GAXRD by depth profiling. So depth profiling in the sense you are scanning one layer to the other. So first you take a very, very low angle. You can see it's a theta omega is 0.45, very low, very low. In that case, you can see the X-ray is only falling on the top surface, zinc oxide. So you are getting the peak corresponds to zinc oxide. You can getting the peaks correspond to zinc oxide. Now omega that is slightly increased. If you now that X-ray is going to CIGA, that coating layer, in between interlayer. So you are getting some additional peak correspond to the second layer signal. So this is from the second layer signal. So now you further increase that mega, so you can go up to the substrate molybdenum one. So you can see the additional peak. This is from molybdenum. So you can get a by non-destructive technique by using that as you do the XPS when you study. In XPS you can get depth profiling by destructive study. But here that depth study can be done in a non-destructive manner. The sample you can still recover, and you can able to identify the structure of the different layer by easily by using grazing angle XRD. Now you can see this is an example of such multi-layer structure: titanium nitride, titanium carbide, again titanium nitride, and tungsten carbide. You see the interface of these two structure. What you can see. So if your X-ray is showing from the top surface, so initially you see there is a peak is here, another peak is here, another peak is here. So three peaks are coming. One is from TIC, another is TICN, another is TIN. So if you see this, what happens? So this titanium nitride, the top layer you can see. So top layer peak you can see here initially. When 2 degree, it is 2 degree. So top layer peak you are able to see here, and that other two, that this titanium nitride top layer you can able to see, and TIC peak is little bit. But later on, when you go inside of the X-ray pulse, you can see how the TIC peak in the second layer is dominant here. Okay, so all those, when you go TICN and interface of the TICN and TIC, you can see you can get an interface zone here, which are the blue and yellow light is overlapping here. So there you are able to get a intermediate structure TICN. So intermetallic structure can also be found using this depth profiling. So if you have a highly oriented structure, you can see that this is a bismuth titanate structure, strontium titanate structure. There you can see the all 004, 006, 008. So all are family of 002 peaks families or 001 peak families. So higher order plane you are able to see 004, 006, 008. They're higher order plane of 002 or 001. So all this, that means that crystal is highly oriented in one direction. So those information you can able to get here depending on the orientation, and also if you have a stress built up in the sample, like you can see that when we were coating on a substrate, so because of multi-layer coating, some stress built up in the sample, and once you have a stress, you can see the peak residual stress, the peak will be shifted depending upon the whether the compressive stress or tensile stress, depending on that peak shifts to either right side of 2 theta or lower side of 2 theta. So you will get all this multi-layer structure or thin layer structure using raging angle XRD. Okay. So another technique, the same like we discussed conventional
Excuse
XRD.
me. So,
Yes, yes,
so I have one question from this.
yes, sir.
Uh, so if you can go back to the setup of the experiment.
Yeah, yes,
So, yeah. So, sir, we have there are two angles involved there. The first is
yes,
omega,
yes,
which is with the plane of the crystal,
yeah,
and the other is theta. So,
theta.
if we denote the axis by x, y, and z, and let's say the crystal is lying in the YZ plane, the angle
Okay.
theta is rotation about the z axis.
Rotation above, that is the detector rotation, the 2 theta, sample to detector, and source to sample, that is your omega.
Okay, so the angle of incidence will not be the same as the angle of diffraction.
Diffraction. So when I am talking about that, I forget to mention actually, when I am talking about thin film, this omega value, that is from the source to sample. Okay. So I am talking about this angle, not this angle.
Okay, sir. Okay, so
Okay.
this is omega and 2 theta is with
2
the
theta is this side.
okay.
Okay.
And
So then
is this the reason this is 2 theta the same as before?
2 theta will remain same. See, 2 theta will be remain same because here your normal direction, if you see, it's not perpendicular, it's slightly changed. Okay, with respect to normal distance. So if this is 2 theta here, so if from normal to here, if this side, if you see diffraction vector, so that angle will be 2 theta other side. But that only this small angle variation that we consider in case of this grazing angle excited. But there is another angle, if you see sample rotation phi is here, and there is psi angle is there. So there are different rotation things are possible here. Only we worried about here this omega. Okay.
So rotate. So if we do the same experiment while rotating about phi,
Yeah,
we'll get information about the orientation of different planes of the plane in
yeah,
different directions.
yeah. That information can get in conventional XRD, but that small rotation is not possible to do in case of a conventional XRD. So you have to do there is another goniometer that will rotate that sample substrate, sample to source.
Okay. Okay.
Okay. So far we discussed that the single crystal XRD. So synchrotron XRD, what I am talking here, it is similar to your conventional XRD. So only thing is, if you go for a synchrotron radiation, that is highly energetic, highly monochromatic, and it has a high brightness. So because of that, you will get very small quantity of sample. You can get better information. For example, like you have a conventional XRD, if you are doping some example with the zinc doping with copper oxide or something, or zinc nickel oxide. So your copper, that whatever the doping element, that will be 2 to 5%. But in case of synchrotron, even 0.1% doping if there, that can also be detected because of his high energetic and monochromatic source. So that you will discuss now. So if you see that this synchrotron is nothing but you have a highly energetic, that this ring type of magnet here. So whatever that electron energy is coming here, so that is by rotation, by multi-layer rotation, you will get sufficient kinetic energy we provide. And because of that, high kinetic energy, a synchrotron is, so it will achieve much higher kinetic energy. So when the energy is very, very high, so whatever that similarly that your wavelength can be, particularly can be highly monochromatic, that wavelength you can get. A synchrotron is a ring which uses magnet. These are magnet, you can see. These are different bending magnet. So they will bend the electrode to slide the X-rays light nearly speed of the light. So the speed of the X-ray or the light is now the speed of the light catches to the speed of light in vacuum. So the such a high speed, so its velocity is very, very high. And synchrotron radiation, that is mainly advanced collimated light, so it's highly collimated with high intensity. And synchrotron produce X-rays that are monochromatic, very high energetic, that means very, very short wavelengths, and right energy for light element like carbon and oxygen. So those light element that we are not able to detect in case of this powder XRD, so those can be also detected, like that the carbon and oxygen information can also get by single synchrotron XRD. So in addition to the conventional XRD, so this will get a pair distribution analysis. A pair distribution is what the information you get, you will give by a particular analysis in that software. You are able to get how that electron density is distributed among the molecule, among the crystal, and thus enabling to find out similarly bond distances, coordination number, all those things you can able to find out. And advantages here, structural characterization of many materials at atomic and molecular level, even a trace level is possible. In addition, you can also combine other technique with XRD. So like that XRD can be combined, so simultaneously you can get multi information. So as I told, synchrotron XRD has a very few particular properties, that is high brightness. High brightness means the brilliance. If you see the X-rays, that is about 10 to the power 5 to 10 to the power 12 order, more intensity. Then highly collimated, since synchrotron light is parallel, therefore spread propagates minimally. It spreads minimally as it propagates, like it's almost parallel, it will propagate, it will not deviate from the path. And it's a wide energy spectrum. So in the radio, you can, depending upon the energy requirement, that wavelength requirement, you can sort out. So you have a wide range spectrum. And because of that, you can combine with other technique with this. Then it just pulse times, very short time is here, and high penetration. The synchrotron provides greater penetration depth than laboratory XRD, is possibly due to because of this highly monochromatic and highly energetic in nature. If you see here, if the sample is here and source is here, it's going through various collimeter, then in between that magnets that velocity, to achieve the velocity, finally to fall in the sample in a similar manner that conventional XRD. But in a synchrotron XRD, the beam line refers to instrumentation that carries synchrotron beam experimental. Like whatever seeing here, this is a parallel beam, this is called a line of beam line that comes, and particular beam is used for in the X-ray analysis. Some other beam will use from other technique. So you have a in between various mirror slits to eliminate those if any other radiation. So it's mainly, if you see, because of this highly monochromatic and high flux and highly collimated, synchrotron radiation has many advantages, like as I told initially. So K alpha 2, so generally K beta is subtracted by using, in case of copper, with nickel filter. So then K alpha 1, K alpha 2, because of that sometimes XRD peak will be slightly split at the top. So those from K alpha 1 and 2. So here no K alpha diffraction in case of synchrotron radiation being highly monochromatic. Here signal to noise ratio 2 is very, very high, and high annular resolution, you will also get better resolution. And you can, as I told, that up to 0.1% weight percent detection limit you can do, and sample can be the 0.1 to 0.5 glass capillary. On that you have to load the sample, and then you will get the structure. So both ex situ and in situ is possible using synchrotron analysis. Like you can do like in situ experiment, like whatever by during temperature, you are applying particular temperature, particular pressure, how the crystal structure changes, phase behavior changes, that in situ you can do. Also, you heat treatment and then you do the different temperature, that the ex situ can be done. If you see here, this is a conventional, XRD and synchrotron XRD difference. You can see this is the red one is laboratory XRD, and the black one peak is synchrotron XRD. You can see some of the peaks that in case of laboratory XRD is just minute, that some phase mutyl anhydride, some phase are there here in, but that is more resolved in case of synchrotron radiation. This is a coal-ash sample. In the coal-ash sample, different multi-phases. So those, very, very small phase you obtain laboratory XRD. So those presence of stress element you can do. Like for example, like some medicine or something, there are some, particular medicine, that some particular impurities there, that very, very stress limit impurity in a particular paracetamol, for example. So there you can easily identify it by using this synchrotron XRD in low concentration. Okay. So diffraction peak obtained from synchrotron XRD are stronger and well resolved. You can see here. Then you can see this is a high temperature synchrotron XRD. Like you are taking 300 to 613 K. You can see how the peak intensity changing from this different peaks are intensity increasing because of crystallinity changes. So those information with respect to temperature you can get, and how the peak is. You can see here the peak initially it is black one is here, then it shifted to lower angle, that 613 K compared to room temperature 300 K. So this shifting is due to some stress or strain. So those type of temperature effect when identified, how the lattice parameter A or C changes. Those information you can also get in conventional XRD, but the synchrotron XRD, as well as both conventional XRD, that high temperature XRD can be taken. You can get better information with this X-ray, diffraction technique. If you have a high pressure, you will take a sample in a diamond cell, that you have to, like this type of sample holder that take. Here the sample is kept here, diamond anvil cell they call. So here, because of the pressure will build up between these two structure. So because of that pressure, how the intensity, that phase changes, how the peak shifting, that pressure is giving the stress strain, this gradual shifting of peak that you are seeing, able to see here. So those information mainly due to the strain or increasing pressure effect that you can get. So as I told, in combination to diffraction, you can other technique when combine, like you can combine diffraction, imaging, and imaging or spectroscopy. For example, that here it's possible that at present it's possible to carry out synchrotron powder XRD experiment with coupled with Raman spectroscopy, X-ray absorption fine structure, that is exams that I will discuss now. So this X-ray absorption fine structure, you mainly get that coordination number and oxidation state. So those things can be combined with the synchrotron XRD. You can get simultaneously energy dispersive time results, that the energy wise you can differentiate the different X-ray energy, and those information you can get mainly using a synchrotron XRD. So X-ray absorption near edge spectroscopy from the exams, that X-rays that will mainly give this is your oxidation state, and exams will go give coordination number. So that we will discuss after some time. So commonly that synchrotron XRD can be combined with many techniques. So that was the main advantage of synchrotron XRD. So far what I discussed mainly on different X-ray based technique. So we will see X-ray diffraction techniques. So next we will discuss X-ray absorption techniques. We'll take 2 to 3 minute break, and then we'll go for this X-ray absorption technique. Okay.
Uh, so just a question before we go for the break. Hello.
Yes. Yes.
Yeah. So my question is that when we talk about synchrotron XRD, uh,
Yes.
just the method of beam, how the beam is made is different. Otherwise, everything is exactly the same.
Yeah, everything exactly is same. Only thing is the beam is a synchrotron generated beam. It is highly energetic and highly monochromatic. So because of that, you are getting there will be the accuracy, all those things you are getting better. Otherwise, this is only the source which is different. Rest is almost same.
So if it is highly monochromatic, it's going to be highly coherent.
Coherent, yes.
So that would give us sharper amplitudes.
Sharper amplitude, and being it's a highly monochromatic, all these things you can eliminate k beta is not there, and even a trace element can be identified.
So what are the energy ranges compared to neutron diffraction? Because if this is high energy, then why do we need a different material, a different beam type?
No. See that in case of synchrotron, the energy beam is widespread, so you can get from visible to X-ray up to that generally. You have a wide spectrum. So depending upon your technique, you want to take UV. UV can also you can do with synchrotron. So you attach that particular wavelength you take out from the beam line and you do a UV. And you take out your Raman like that particular band and you do a Raman spectra. And similarly, you take your X-ray range, you do for the X-ray. So that is there. But if you go to neutron diffraction mostly that those things, the wavelength is fixed around lambda is around like in Dhruva we have around 5.4 angstrom or something in that range, 4 to 5 angstrom in that wavelength lambda. So that is only that is almost fixed. That you can't vary. That wavelength you can't vary in a neutron diffraction technique or
And
in
so,
a no, yeah.
which one is more energetic?
uh, Neutron and X-ray, if you see, I'm not exactly sure, but I think that these two are X-ray and neutron complementary technique. So X-ray may be highly energetic in comparison to neutron, but I'm not sure. You have to check it exactly. But those two techniques are complementary. Some information you get from XRD, that information you may not get from neutron. Like for example, neutron diffraction being a magnetic moment, you can able to see the magnetic ordering. Okay, magnetic information get, but in X-ray you can't get any magnetic information. So those are complementary technique: X-ray diffraction and neutron diffraction. I will discuss neutron at towards the end if time permit. Okay.
Okay.
So we'll discuss now this X-ray absorption technique. So it's the only difference X-ray absorption and X-ray diffraction. If you come that there, it's Bragg's law satisfied. Then we see the X-ray diffraction mainly when X-ray absorption that whatever the incident X-ray energy has to absorb, and after absorption, the core electron usually come out from that as a absorption process. Or then second thing is that X-ray spectroscopy, how that the incident X-ray gives you X-ray fluorescence. So in X-ray absorption technique, if you see there is a divided two part. One is X-ray absorption near edge structure and extended X-ray absorption fine structure. So exgenase and exapse, these two techniques in case of X-ray absorption spectroscopy. So if you see the X-ray absorption spectroscopy. So as you know that intensity of X-ray, that if I falling on this sample substrate, this I, then that I0 is falling, then after that passing through the X-ray, the sample is for the X-ray radiation passing through the sample, the intensity will be I0 into e to the power minus mu x. So mu is your attenuation coefficient that you discussed in the beginning, and this mu depends on the X-ray energy. What is the energy of the X-ray? That means that how much energy will be absorbed, and how much will be transmitted through this sample. So that depends upon the attenuation coefficient. So that mu that mainly varies with respect to X-ray energy. If a high energy, your absorption will be low, it's mostly transmitted, and high Z and low Z. If it's high Z material, it will absorption varies according to the atomic number, then density of the material, the atomic mass. So similarly, mu is equal to rho z to the power fourth order to the e to the power 3. So once X-ray absorbed, it's mainly that we discussed at the beginning, the photoelectric effect. So that X-ray absorption spectroscopy mainly based on the photoelectric effect, that the incident X-ray beam is the sample substrate. The incident X-ray beam will fall the sample and it will knock out an electron from there. So this is the X-ray falling, that will get absorbed and an electron will be coming out with this. That it depends upon how this electron is binding on the orbital. That depends on the binding energy and this kinetic energy of the particular material. That will depend upon the this binding energy of the core electron as well as the h nu, that electron source. That X-ray energy, photon energy that is falling on this. So if you see the absorption process is a high, the incident X-rays are energetic enough. So if you have, this is the core electron 1s orbital. In the 1s orbital, if you see that the core electron incident X-ray is falling on this. So because of this energy will absorb, and this electron will knock out from the core orbital. So either it will go to the continuum, or it will go to the unoccupied higher orbital state, or it will go to the vacuum. So depending upon the energy, how much incident energy you are falling on the sample substrate, is decide whether to go to the unoccupied states or it will go beyond that. So if you see excitation of core electron into higher unoccupied energy states, or ionization occurs, or it can go to the continuum unbound state, it will go. So extensively sensitive to the chemical state and local environment. That means if you see here K cell, L cell, M cell, depending upon this, whether 1s orbital is going to here to from K cell, that K, if it is going for 2s1, 2s2, either L1, L2 or L3, you can name. This is the absorption. That means when that particular this electron is moving here, so in the core, so once that particular energy comes, so the energy matches, then only this electron will jump to the core to the unoccupied state. So because of this, the absorption actually absorption coefficient suddenly there is a random change. So because of that, you will see that there is an absorption edge, like here K cell you can see here. So once the absorption edge appears, that core electron matches with that of X-ray photon energy, so it will you see there is an absorption. Similarly here you will see that absorption coefficient will randomly it will changes, and you will see a band edge peak. It's necessarily the energy, the binding energy of the co-electron transition is attained, the mass absorption coefficient increase. So one, as I told, that once energy, when the necessary energy, that is the binding energy for a core electron, transition is attained, there is a transition takes place, the mass absorption coefficient mu increases sharply, and you will be able to see this absorption edge. And each edge occurs of its own critical absorption, like K cell, L cell, and K cell of a copper or a nickel, or L cell of a manganese or a nickel. They are different. You can see the Fe, the K is 7.1, nickel K is 8.3, and molybdenum is 20. But high Z material, you can see 20.3. So all these elements, K cell and L cell, the energy are different. So that's characteristic to the particular element. So we are measuring this energy, that band edge, you can identify the particular element, and it's information about bond strength, bond length, neighboring atoms, like it's a tetrahedrally coordinated, octahedrally coordinated, all those information you can get. And edges, like you can able to see that the edges are labeled according to the cell where the core electron lies, at K cell, L cell, depending upon that. And you see here, if you see X-ray absorption fine structure, that mainly modulation of X-ray absorption coefficient at energy near and above X-ray absorption. Like if I'll discuss first this one, you can see here. So this is your core electron. So there you can see one electron is knocking out from the outer orbital. So one case is going to the unoccupied vacancy state. If you're low energy, if not enough energy, your incident X-ray is not having enough energy, it will knock out, completely knock out. So it will go to the unoccupied state. That is low energy X-ray information will get. X-ray absorption near edge spectroscopy. If it is too high, like its energy is too high, then it will go to the scatter process. Only it will high energy, so it will knock out from the completely knock out from the orbital. So there it will exact study X-ray, extended X-ray absorption fine structure. If it is a medium energy, just enough to escape the continuum, like just over to go to the vacant orbital, the continuum space. So in that case, you get that X-ray absorption near edge spectroscopy. So if you see that this when that this is an spectrum from the atom, when the X-ray or some that X-ray emits that the electron is coming out from the core, so it propagates in a that's spherical wave. It propagates. And so, for example, that X-ray is coming that time, falling on this core electron, and there are many other electrons nearby. The electron cloud of this electron and this X-ray, so the another electron is here, so they will over interference each other. So because that whole X-ray absorption technique is based upon the interference, whether there is a single atom or is a multi-atom interference. So because of that, you will see the fine structure absorption changes. Like core electron propagates in spherical waves. As you know, that way generally expressed in wave vector k equal to 2 pi by lambda, and kinetic energy equal to that. You can use this equation, you can find out E kinetic equal to what is the photon energy you apply h nu minus E0, that's the original energy. So k, if you express the 2 pi by h whole square 2m h nu by E0. So here it generally since it's a we were discussing about the interaction between the wave interaction here. In case of X-ray absorption spectroscopy, we express it in a k wave vector terminology. Okay. So if you see here, this is the one observing atom here, X-ray is falling here. So there is no neighboring atom, only one single free atom is here. So because of this absorption here, so once whatever the incident ray is coming, that matches with the binding energy of the core electron, so that will knock out. So then we will see there is a absorption edge, that mass absorption coefficient randomly changes. You will get just a sharp this type of transition. You will get E versus absorption probability if you see. So that case there is no other nearby electron, it will not interact with each other. So here you can see the spherical wave, that is E is large enough to promote the core electron to the continuum. There is a sharp change in absorption here. So isolated atom, that mu E, that energy, you will see get a sharp probability of transition will be energy propagation will be sharp here. And if there is a neighboring atom near, there is a blue atom here, this is a red atom. So you see after this transition to the wave vector of this blue atom and this red atom, this will go and it will interact with the other atom, it can again bounce back, it can propagate back to this. So there is a interference takes place in this case of there is a two neighboring atom, can see here one is here other, so their wave vector they are interacting with each other. That is that this X-ray absorption spectroscopy is an interference effect of photoelectron with each other. Okay. So you see, if you see the typical X-ray absorption spectroscopy, you can see here. So this is the initial one, that before the pre-age. Then there is a transition here. Then it is the other one. So the absorption mainly occurs. This is the near edge absorption. You can see just before the sharp absorption, you have a pre-age absorption, and then you go a sharp transition here, and then you have a small like this type of amplitude, like looks like some wavy structure here. So mainly that the electronic information you will get from pre-age as well as this fine age structure in this, that mainly gives that your exynous part, X-ray absorption near age spectroscopy, that will give you oxidation state, and then you go to this this wavy structure part, so that gives mainly geometric information. That means whether the coordination number, those information you will get from the exams. So if you see, the sharp edge and the pre-edge resonance are characteristic of the local symmetry of atom. So here this will give the local symmetry like oxidation state, and then they can use a fingerprint to identification of local structure, and then the X-ray absorption pre-age extended very few. The energy will be from this to this, the energy will be within 40 electron volt energy, but beyond this you will get extra absorption fine structure. So in exams you can identify their sensitivity, chromium +3 and chromium +6. So chromium +3 and one is octahedral and one will be like tetrahedral coordination. So because of that, oxidation state difference, you can see that pre-absorption structure is different. That we'll see in next slide. If you see the information what you get, then you can see here this is the energy versus mu, that mass attenuation factor, and then you can see from here to here only about 40 to 30 to 40 electron volt. So that is only the exyness. Beyond this to this is about 40 electron volt. So that you will give exyness, and beyond that, that 40 to 1000 fast here in this range you will get exam spectroscopy. So you see here in exyness there is a 3 electron I have shown here, and here blue, red and green. So their interference you will get. So that means when you have a neighboring atom, so exyness you will see this sharp transition which you will see, that is because of the neighboring electron coordination. So that way, that's why you will get the information about sensitivity of the symmetry of the neighboring atom, valency band structure you will able to get. And in case of this higher one, the direct one interaction, so you will give that sensitive to the local environment. So how closer to each other, so those distance like you can measure here, bond length, coordination number, so those things you can measure here. So as I told here, you can see how the wave vector are interacting with each other, and if you have a long range interference, that dominated by multiple scattering. This is a multiple scattering. So this multiple scattering mainly occurs in finite structure. The sharp band transition is multiple scattering, that will give the multiple scattering make near edge spectra sensitive mainly to the symmetry of the atomic arrangement information, and can be used to indicate the kind of bond symmetry, whether it's a tetrahedral, octahedral symmetry, and also electronic bond structure calculation. So all those information you can get, valency information, indicator of valency band, that oxidation state, those information you can get from a fine structure. But you go to the extended absorption, that spectroscopy instead of near band edge. So here only direct two atom interaction. So photoelectron from one atom being scattered by the neighboring atom. So there will be interference, and from that interference, what you will get mainly that information about the immediate local environment, like how the coordination number, whether it's octahedral, tetrahedral coordination, whether how many atoms are surrounded to that position. So those information you will able to get from the exam study. So mostly that the exyness and exam. So whatever you are getting in exyness, that the X-ray absorption near end spectroscopy, mainly you get oxidation state. So those information you get from X-ray photoelectron spectroscopy. So that information you will get from this exyness. But the additional information you will get from exams is you get your bond length, bond ordering. Those information normally you don't get in any this XPS technique. Okay, if you see, once you get the X-ray spectroscopy, it will look like this, like initially it's going parallel straight, and then there is a sharp absorption. Because of this absorption, once you achieve that particular binding energy of the X-ray, binding energy of the electron matches with the X-ray photon, so you see the sharp transition, and then there is a up down that wavy patterns. So here, first for analysis part, first you have to take that pre-edge, you have to take the background. This pre-edge, that straight line has to subtracted. So after subtracting the post-edge separation, you will get a better spectra that mu g this. Then that absorption coefficient, that what you get. So you will remove the oscillation parts. In the oscillation part that I told, this is from EXAFS, that extended absorption fine structure. So that you remove, and then you have to take a E0. That is the equation is wave vector k equal to that h nu minus E0. This E0 is maximum when it's first derivative of this. So you do a first derivative, you will get that peak position sharp peaks from that band edge you will able to get, and you can find out that what is the particular band energy. From there, there you can find out that oxidation state of the element. Example, I have shown here chromium plus 6 and chromium plus 3. You can see here chromium plus 6 is here and chromium 6 plus 3. You can see the one is the tetrahedral octahedral coordination, and those difference, because of that, in case of octahedral, this chromium plus 3 and this and chromium plus tetrahedral coordination, you can see there is a additional, this is a sharp peak, that near edge peak here in chromium plus 6, that is absent in case of chromium plus 3. So the richness of chromium 3 and chromium 4 show a dramatic dependence on the oxidation state and coordination chemistry. For example, that for ions with particularly partially filled D cell, there is a PD hybridization changes, and because of these changes, that the large tetrahedral coordination, that there is a changes in octahedral dissort and very large tetrahedral coordination. You get those information you will get from this absorption fine near edge spectroscopy, and see that it will mainly give the oxidation state. I told you can see chromium metal to chromium calcium chromate. The chromium exists in different oxidation state. You can see in the chromium metal, chromium 0, you are not able to see these peaks. So these peaks you are getting when chromium in higher oxidation state. When chromium Cr2O3, here you are not also getting that small peak, but here there is absorption peak. That is because of in higher oxidation state, you will able to get. So detailed explanation I have shown here that I'm not discussing. So mainly you can identify by using Agnes spectra. Here is chromium Cr2O3 or chromium metal sample. So those information you can able to get equivalent to this X-ray absorption, that X-ray photoelectron spectroscopy. Then this interpretation of EXAFS is little complicated than Agnes. So that this part I'll not cover much. So if this is the equation, that whatever the wave vector we are getting, so that is Fourier transformation from K space to R space used to do, and then there is a model. From the model fitting, you will get amplitude and phase shift delta, and you have a mean free path lambda. So all these variation will be, you will see, and finally wave vector equation you can fit, and you can get a Z EXAFS sensitive to Z of material. So because of all those parameters, what you will get, mainly you get photo energy versus mu float. Once you get photo energy plus photon energy versus mu float, so then you convert to this photon energy, that mu e attenuation energy to chi e, you have to convert. So then once you convert it, so you can easily either k versus k, that chi square versus k, or k square versus k you plot, so you'll get this type of peak. So Zn zinc kh peak, so you can see what is the peak position. From there you can find out that what is the bond length. You can get all information, like I have given just one example. This is zinc oxide with manganese doping with zinc and oxygen, and zinc. You can see here zinc oxygen bond length 3.86. So this peak is mainly due to zinc oxygen ZNO peak, and then zinc peak. That other information you will get, that there is another peak here, that is also will show whether there is a how manganese doping is changing the you can see here the bond length is 1 point something, so here is shifting to higher. So because of manganese doping, how the your C axis and C and A, that changes 1.94 to 95, or those changes 3.86. So whatever the changes, those changes are quite low here, but you can able to see those band information by using this exact studies. Okay, so mainly if you see the X-ray absorption spectroscopy, so mostly it has to, it can be done only it's positive with a synchrotron source. When there is a synchrotron source, then only you can do this X-ray absorption fine structure analysis, that is a X-ray absorption near spectroscopy or extended absorption fine structure, that is possible with a synchrotron source. Normal conventionally it's not possible. So conventionally you can do only an X-ray absorption spectroscopy to an extent, but it's far this absorption, all those study you need and synchrotron source. So like absorption, another technique that is called, I'll just take 2-3 minutes for this X-ray fluorescence technique. So it's similar to X-ray absorption, but the only thing is there during absorption you are studying here, like once it goes to the excited state, from there it's going back to the ground state, there is like some emission is occur. So that emission is here in the term of fluorescence. So that emission energy that you will see here, emission property you will see in case of X-ray fluorescence spectroscopy. That means you have excited core holes that you can see here. Once X-ray energy falls on the sample's core electron, so this X-ray will go to the higher level, and from the higher it will, after some time it relax to the ground state. So it will from field 3D orbital will come, the core electron will come back, you will see a fluorescent emission. So those fluorescent emission you will see. The excited core hole will relax back to the ground state by transition of a higher level electron into the core hole. Since that core hole is lower energy position, it is a higher energy position, but you will see some energy will be emitted here, excess energy emitted, that is as a fluorescent X-ray. So the X-ray energy fluorescent is characteristic of that particular observing element. Like for copper, nickel, zinc, all these X-ray fluorescence energy is different. So here you can do both qualitative as well as quantitative analysis. Like if you have proper standard, you take a known sample and do all this elemental analysis. You can once you have refined your calibration curve you flood, then you can easily find out what are the different element, what is the composition of each, concentration of each element, that can be possible to measure by X-ray fluorescence spectroscopy, which is almost equivalent like we do generally ICP analysis, inductive coupled ICP AES, atomic energy spectroscopy, that elemental analysis we do with the ICP AES. So here in the XRF also you can do those element analysis. Only thing is you need a good standard. So once you have a standard element, then you can able to identify all those constituents with that help of the standard. So if you see the instrumentation part, here it's almost similar to that of XRD. Only thing is here you can see the X-ray tube is falling on the specimen. After specimen, in case of XRD, directly goes to detector. Here is the detector in case of XRD. But here, in case of fluorescence, instead of going XRD, this whatever the X-ray is emitting from the specimen, that will go for an analyzing crystal. So this part is extra, that analyzing crystal is there. So that analyzing crystal, what will do, this analyzing crystal will analyze this X-ray emitting of the sample, and it will separate into them, say, by the energy or in the frequency manner. Like it can be by wavelength, that can be separated, or by energy, that can be separated, that from the analyzing crystal. Then detector will identify that element, and it will say how much nickel K alpha is there, how much cobalt K alpha is there. As I told, that two types of X-ray spectroscopy are available. One is X-ray, that the energy dispersive X-ray XRF, another is wavelength dispersive XRF. So here important thing, no elemental analysis, no need of crystalline sample, and it is non-destructive and very fast process to get elemental analysis. So elemental analysis is possible without any, whether it's crystalline, amorphous sample, it can be easily that the energy dispersive, that analyzing crystal can be differentiate all those energy levels or by energy wise or wavelength wise. If you see EDAX, that is energy dispersive X-ray fluorescence, that separate X-ray according to their energy. But in case of wavelength, separate X-ray according to their wavelength, and energy dispersive here, that is you have a multi-channel analyzer is used. Here on all element in samples are excited simultaneously. So whatever the element present in the crystal here, so all element will come out from here. Then this analyzing crystal will differentiate them, separate them, and send to the detector. So better efficiency will get detected without being separated. In case of EDAX with EDXRF, you will able to see detected without separation of the each element. But in this case, X-ray directed to the crystal, which diffracted X-ray in different according to wavelength. So that means here what happens, whatever the X-ray is coming here, so it will diffracted with the separate wavelength. It will separated, and then better resolution but lower efficiency, since that here that component is moving. So that arrangement is for that. In that case, in wavelength wise, that is fixed position, here it is a movable. So because you have a two way of EDAX analysis, or that like in SEM, transmission electron microscope, or sorry, scanning electron microscope, or TMS, transmission electron microscope. You also, there is the EDAX analysis, EDAX. That the EDAX is nothing but energy dispersive X-ray absorption process, X-ray analysis that will separate your each element by energy wise. So it is similar. EDAX XRF, EDXRF is similar to that. So mainly we cover that this X-ray based techniques till today. In the next class, I thought I will cover that neutron diffraction, that due to time doesn't permit, so I'm not going that. So if you see the typical XRF spectrum here, you can see that this is a milk powder. You can see potassium, silver, cobalt, all those elements can be identified by using that XRF. This is a milk sample that contains some potassium 40, K40. So K40 is radioactive, so that is not allowed. To identify that particular K40 is present or not, so this XRF was done. You can see all elements except hydrogen, helium, lithium can be detected using XRF, and detection limit is very, very less with 0.01%. But some problem is that it has an interference effect, that since its wavelength was separating, some spectra overlapping is possible. Overlapping of K line, L line is possible, and environmental interference like some sodium, chlorine, that light element emit weak fluorescence, that is not feasible to detect it, because that is attenuated with air or argon atmosphere inside the chamber, and there is a matrix information interference absorption enhancement effect. Sometimes because of the chamber, that all those gaseous elements are there, sometimes that absorption enhancement occurs, so that will interfere. So but you can do many evaluating the KL spectra, Rayleigh scattering effect, Compton scatter, this then Bremsstrahlung radiation, all those things, if you taken care, you can able to identify, comparing area under the peak. So what are the area under this peak? Once you calculate that area, you can able to find out that what is the percentage of each element. So you have to take absorption, any element that absorb scattered fluorescence. If some absorption occurs, that will also interfere. So that, but typically if you see, you will get a quantification data up to at least 95% accuracy with using this typical X-ray fluorescence spectroscopy. So we have covered X-ray diffraction, X-ray absorption, and X-ray fluorescence spectroscopy. So I suppose to finish this neutron diffraction, that we'll discuss after a few class when you get time. So in next class, we'll start from single piece. This two new technique: the small angle X-ray scattering and small angle neutron scattering with neutron diffraction. So I have covered X-ray diffraction. There is another thing is scattering techniques. So how this scattering technique is helpful to useful to measure the particle size, that we will discuss, and how neutron diffraction gives the complementary information to the XRD. So that we will discuss in next class. Okay. So if there is any questions, you can raise here. Otherwise, you can ask me question by email, or you can discuss in next lecture.
Excuse me, sir.
Yes.
Sir, good afternoon. Sir, I was saying that when will be our exams? Like, there was some exam schedule. I mean, after
Yeah,
the
yeah.
classes.
Yeah, the exam is like that. Towards the end of the class, I will give some assignment.
Okay.
Okay. So the exam is divided into two parts. One is your assignment, other is your viva. But there is no written exam in this
Okay,
course,
sir.
since there are many students are attending from outside the BRC and outside HBNI.
Okay.
So no written exam is there. The assignment you have to submit. We will give us some time that one or two assignment for each module we will give.
Hmm.
So the assignment is 50% weightage and 50% weightage will be your viva course. So that will be done at the viva will be done at the end of the whole course. Most
So,
probably I think
the end means around December.
somewhere in December because the course will
Okay.
complete I think December end. So I
Hmm.
think December end or somewhere that time it will be viva. So those who are from locally from Mumbai region or BRC, so they have to attend that viva physically. Outside
Okay.
member can give online.
Okay. 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 Thank you so much, sir.
So
Yes, yes.
so there was one request. I'm not sure if it will be accepted or not, but uh, when like just before minutes before the class starts, can the slide that you will be using be uploaded? Because then it will be easier to annotate on it while you are teaching.
Okay. So because
If it if
yeah,
it's possible.
I understand your query. So we see, I used to send slides to HBNI, then they used to take care of that. So I'll talk to them. I'll find out if possible they will upload it before. But the problem is that you see there are 90 students registered, and I'm able to see only 30 to 40 students are attending. So if the problem is if you will upload the slides before, then even that 30 student may not come. Okay, so I'll discuss this with the HBNI if they allow me, and then I will upload it before class. Otherwise, all slides are going to be uploaded after class.
Yes,
Okay.
sir. After the class, it's possible, but I'm saying like if we
Yeah,
have
yeah.
it on hand, it's easier to annotate on it,
Yeah, sure, sure.
write on it.
I'll discuss with our team member that HBNI. If they allow me, then I will upload on the website. Okay.
Okay, sir. That'll be
On
thankful.
the media
Thank you,
site.
sir.
Okay. Okay,
Sure.
because the time is because my course content is quite large and time classes is less, so that's why I'm going little fast. If you are from VRC or nearby, then you can directly come and discuss at any time. That is not any problem. Otherwise, if anybody has doubt, they can mail me. We can have a separate discussion. Okay.